Okay, so previously we have discussed RSA codes in chapter 15. Now we are going to talk about again an interesting thing known as the counting and choosing. So mathematics has many tools for counting, and we shall give some simple methods in this chapter. These leads us to binomial coefficients and then to the binomial theorem and the multinomial theorem. So let's begin with an example. So let's begin with an example, or like I should write, we will discuss one binomial coefficients, two binomial theorem, three multinomial theorem. Okay, we will begin with an example. So the example says a security system uses passwords. Passwords consisting of two letters followed by two digits. Okay. How many different passwords are possible? Right. So solution or answer to this one is the number of choices for each letter is 26. So for each letter, we have 26 choices. For each number, we have 10 choices. Right? We claim the answer is the product of these numbers. Which numbers? Like 26 multiply 26 multiply 10 multiply 10. This is the answer. The product of all these numbers is the answer to the question. Okay. Here's the justification for this claim. So we say that, so let's say justification. Let n be the number of possible passwords. Right? And let a typical password be P, that there is alpha, beta, gamma, delta, where alpha, comma, beta are letters and gamma, comma, delta are digits. Right? For each choice of alpha, beta, gamma, alpha, beta, gamma, there are 10 passwords. Passwords, say alpha, beta, gamma, delta. One for each. How? Like one for each of the 10 possibilities for delta. Thus, we can write that n is nothing but 10 multiply number of choices for alpha, beta, gamma. Number of choices for alpha, beta, gamma. Likewise, for each choice of alpha, beta, there are 10 possibilities for alpha, beta, gamma. So we again have n is 10 multiply 10 multiply number of choices for alpha, beta. Perfect. Now for each choice of alpha, there are 26 possibilities for alpha, beta. So for each choice of alpha, there are 26 possibilities for alpha, beta. So n is going to be 10 multiply 10 multiply 26 multiply number of choices for alpha, and then it is going to be 10 multiply 10 multiply 26 multiply 26. This is how we claim the answer, like come up with this answer. Okay, perfect. Now The argument used here in the above example is nothing but the following result, and we call it mathematical principle, multiplication principle. Wait, let's write it because this is theorem. Theorem 16.1, multiplication principle. Right. Okay. And this says that let P be a process which consists of n stages. P be a process which consists of n stages and suppose that for each r, the rth stage can be carried out in AR ways. Then P can be carried out in A1, A2, A3 to AR ways. This is the multiplication process. So in above example, there are 4 stages with comma A3, A4 is 10. Okay. Let's talk about another example. (16.2) says that using the digits 1, 2 up to 9, how many two-digit numbers are there with 2 different digits. Okay. Right. So the solution will be, we consider the following two-stage process to pick such an even integer Okay, there's a condition that how many even two-digit numbers. So we'll consider that the following two-stage process to pick such an even integer. First stage is to choose the second digit. The first stage to pick is to choose the second digit. Because we are choosing an even integer, the second digit could be 2, 4, 6, 8. It can be done in four ways. It can be done in four ways. The second digit is to choose, the second stage is to choose the first digit, which can be done in 8 ways. The second stage is to choose first digit, which can be done in 8 ways. Now you must be thinking there are 9 numbers. Why there are 8 ways? Because we need to choose two different digits. So if you are choosing one, like if you are choosing 2, 4, 6, or 8, any of them digit is a second digit. You can't choose them as a first digit. So that's why there are. So at one point, if you have 2 in the second digit, you can't have 2 in the first digit. So you will have any other except 2. So there are from these 1 to 9. So that's why there are 8 ways. Hence, by multiplication principle, the answer we have 8 multiply 4, which is 32 even two digit numbers. 32 even two digit numbers with two different digits. Right. Remember, if we would have carried out the process the other way around, and first choosing the first digit, then because then the number of ways of choosing the second digit would depend on whether the first digit was even or odd. So that would be a trouble. Okay. Now let's talk about another thing in the similar way, and that is proposition 16.1. It says that let S be a set consisting of n elements. Then the number of different arrangements arrangements of the elements of S is order in order is elements of S in order is n factorial. And recall that n factorial is nothing but n into n minus 1, n minus 2, up to 2 into 1. Okay, right. So example, we say that if S is a set which contains A, B, C, then the different arrangements of the elements in order are then the different arrangements of the elements in order are A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Is predicted by the proposition that it can be 3 factorial, which is 6. There are 6 of them. And we can prove this proposition. So choosing an arrangement is an n-stage process. Choosing an arrangement is an n-stage process. First, choose the first element. First, choose the first element and possibilities. Then choose the second element and that have, and this can be any of the remaining n minus 1 elements. This can be any of the remaining n minus 1 elements. So there are n minus 1 possibilities. Then the third. For which there are n minus 2 possibilities. right? And so on. Hence, by the multiplication principle, the total number of arrangements is n into n minus 1, n minus 2, dot dot 2 into 1, which is nothing but n factorial. And that is the proof of our theorem. Perfect. Here we will end this part of this lecture. We'll talk in the different one about the binomial coefficients and binomial theorem.